Hello, thanks for coming. Do you hear me okay or? Sorry. Maybe like this. Yeah. Okay. So we're gonna talk about prompt engineering, addressing the sensitivity of large language models. Uh, First, let me find the mouse. Okay. A little bit about myself. I started out as a software engineer, been that for about 10 years. For the past 5 years, I moved to machine learning. Uh, Worked at a couple of startups and kind of settled on Mantis NLP because they are great. A bit about Mantis. We are a remote NLP consultancy. Um, the team is all over Europe. Mantis was started a bit less than 2 years ago. And since the inception, we valued open source and worked on ethical and reproducible data science. It's been quite a busy 2 years. We touch on most of the NLP tasks. A little overview about what we're going to talk about. So we're going to look a bit about how do you run and interact with large language models. What is a prompt and how you construct prompts. We're going to look a bit at our experiment setup, and then just we'll look at the highlights of what we found based on those experiments. So, large language models. For those of you that aren't that familiar with them, large language models are these ginormous models trained on very big data, like models that are multi-billion parameters ones. It's pretty funny that the whole of Wikipedia is now considered quite a small data set compared to the data sets that these models were trained on. For example, the smallest model that we experimented with, GPT-J, 6 billion model. Comparison to that, BERT is 350 million. And of course, we have the one at the next, at the other end of the spectrum, GPT-3, which is 175 billion. There are other bigger models, but that's where we settled. Another thing about these large language models, recently they have been adopted quite a lot in actually working directly on NLP tasks. So because they are very big, and they become quite good at kind of everything, so people started using them to resolve these NLP tasks with just very few examples. We joke around the team that, pretty soon we'll have to find other jobs because GPT-3 takes over. So, part true, part not. So how do we interact with these large language models? We used mostly these three approaches. First one, of course, you call some APIs, and the model is provided by someone. Second, you either use some kind of Hugging Face Accelerate for helping you deal with the model, or Deep Speed MII more recently. Regarding the APIs, for example, these are the ones that we used in our experiment. OpenAI for the 3 versions of GPT that we tested. Hugging Face Inference, you can host actually quite a lot of models there, but not so much in the large models space. Not yet, at least. They are working on it quite actively. We used it for Bloom. AI21 Labs for Jurassic 1 Jumbo. It's another very big model. Cohere, we tested the X large model. And Goose AI, I found it for GPT Neo X 20 billion. But you know, the APIs can be quite expensive, especially if you want you want a lot of requests for them. So the other approach, you know, is to do something like Hugging Face Accelerate on your own private infrastructure. In theory, you would only need, like, to load the model, you will only need the code on the left, right? But a bit of fair warning, Accelerate and Hugging Face integration is under active development, so it's still, there are still a few kicks to sort out. Most of these actually have already been solved by the time of this talk, but you know, I'm still highlighting what the problem we had was. So for example, for OPT models, for some reason, you needed to load the basic model part and the additional head layer separately. Couldn't really tell you why. It's very important to do that last step, you know, with tie weights, because that makes sure that everything will stay in the same place and no funny business is happening. And most of the time, like, Accelerate automatically fills the GPU memory, right? And then if you still have layers left from the big model, it fills the CPU and then even more the disk and so on. You want to make sure to leave some space on the GPU. It doesn't necessarily make sure automatically, you know. So for example, if you have, let's say, more than 500 tokens when you generate, it's usually a very good thing to manually adjust a bit the device map to leave some space on one of the GPUs, you know. Because if not, you'll just get the OAM, and reloading the model takes quite a bit of time. But this has actually been sorted quite a bit recently. Like now you just have to do this max memory thing and say for each GPU, hey, use just this amount, right? Like for example, in our case, this is a 2 GPU instance with 24 gigabytes each GPU. And I said, you know, leave like 6 gigabytes leave for when you actually call the generate function. But you know, enough of that, about that. Let's actually focus on prompts. So what are prompts? You use prompts to interact with the models, right? A prompt is the input given to the generation function meant to guide the model to generate the desired output. The concept of prompt engineering itself is relatively new, but I've seen it being gaining popularity quite a lot. I think that is because when you start playing with these large language models, you start realizing that it kind of takes the place of feature engineering, what we did before in feature engineering. Part of this talk is meant to show that, yes, it's really as important as feature engineering was before. So how do you actually construct the prompts? Usually follow some kind of schema similar to this. At first, you need to describe the task that you're trying to solve, right? You see it in green. For example, this example you see here is the very simplest case we used in one of the tasks we tested, text classification. So you just say, classify into 4 labels, you know, anger, joy, optimism, sadness. It's very good to have some kind of input indicator, in this case, text. The input itself, whatever it is, you know, and output indicator again. It's good in general to keep them separate and clean. But of course, most of the times you won't zero-shot the problem, right? You'll give some examples to the model so it can figure out what you're actually trying to do. N shot being, you know, n the number of examples you give. And it's the same thing, right? For each example, you have the input indicator, the input-output indicator. And in case of the examples, of course, you also give it the output itself, right? A couple of prompt construction guidelines. Make sure the description of the task is pretty clear and don't use any fancy words as much as possible. If necessary, include specifics, but gradually while testing. Very important to have clear markers for all the parts of the prompt, right? So make sure to separate the task description from the input and so on. Usually that only means, like some new lines, but in other cases, you can get more creative with, new line plus some vertical bars and so on, just to format a bit to let the model know, hey, this is something you'll see over and over again. This is a clear separation of things. And quite an important thing here is the end-shot representation should be quite diverse, right? What I mean by this is, let's say for the task classification task, we give it 3 examples, right? So 3 end-shot. It's not gonna help if all the examples have the same output, right? Like before, I give it 3 examples, all with the output sadness. For most models, especially the smaller ones, you'll see that they kind of think that, hey, this is a pattern. I'll always respond with sadness no matter what you give me, right? GPT-3 and some other bigger models kind of are smarter a bit, but even they can get messed up by this thing. Also, like at the beginning here, let's say you give examples, but in the order you gave them there, again, like it might think that, hey, you gave me these examples in the order here. Now you probably want them in the same order. So you have to think a bit about that when you deal with end shots. Also, when you call the actual generation function, either locally or in an API, it's still the same things apply. I found you should be very careful of the following things. 1, trailing spaces, just remove them, Don't make sure there is none, because you won't know why the output is just gibberish. The use of max tokens is quite important. I'll again use the example of the text classification. If you would use a big max tokens number, like let's say 10 or 100 or something, the model might understand that, hey, I need to generate something else here than just a label, right? So in our case, we used 3, for example, for text classification. Why 3 and not 1? Usually, the first token that it predicts is the space character, actually. Then the other 2, because, for example, sadness is 2 tokens, right? Not 1, sad and ness. So you have to think about that, because if not, you won't understand why, hey, I put max tokens 2. I always get as response sad and not sadness. What's the matter, right? Formatting of the labels matters. Make sure the output that you expect is quite clean, and the words are quite normal and easy for the models to understand. And the usual parameters that you give the generation function are also quite important. Top P, top K, and temperature usually. We rarely use the greedy approach anymore. Let's look a bit at the evaluation setup. So we selected 12 large language models for our experiment. Jurassic 1 Jumbo, Bloom, GPT Da Vinci, Cohere, the X large version, the biggest one they have, OPT from Facebook, the 30 billion version, and later the 13, NeoX 20 billion, UL2 from Google, another GPT smaller version, Flantify, which just appeared recently, and another GPT-3 and GPT J6 billion. These are ordered by size, right? keep in mind this because the next graphs you'll see will also have the models ordered by size. So for each of those models, we settled on five of the most common NLP tasks. Text classification, name identity recognition, similarity, QA, and summarization. I would point out that we tried to select some data sets for them that weren't the simplest ones. We wanted to give the models a bit of a challenge. Wasn't the case for every data set, but yeah. And so for each task, we constructed 5 prompts. We did it kind of empirically, trying for each prompt to raise its quality and complexity. Depending on the tasks, we used multiple shots. For text classification, we used 1, 3, 5, and 10 shot. NER, similarity, and QA 1, 3, and 5. And summarization only 0 and 1 because of length constraints. An important asterisk to mention here is we only tested on quite a small sample from each data set, 100. That's mostly because of cost constraints. It's very expensive to experiment with all of these combinations. I would mention, though, that we did test for 50, 100, 200, 300, and saw that the score kind of settles at 100. So we selected that as the basis. Right. So next we'll look at some takeaways based on the experiments we did, what we found from them. The biggest one and the one that I actually care that you remember the most is prompt quality actually matters. We have here a graph showing just a few models. For each model, we have the different prompts ordered by kind of their complexity. We can see that not necessarily more complex means the better always, But I think the main takeaway here is that the difference in some of these cases is 2x, even 3x better score, right? So that's pretty amazing. And that should show the value of prompt engineering just there, right? If that isn't enough to convince you, maybe this will. With the right prompts, we actually managed to beat a very big model with GPT-DaVinci is one of the biggest models we tested on, and GPT-J is the smallest one, right? And with the right prompt, it managed to surpass the results from GPT-3. Again, that 100 sample is something to keep in mind, but still pretty amazing. The error bar that you see there is basically the difference between the prompt scores. So of course, GPT-3 was more stable, and you saw how big the difference was for the smaller models. Next takeaway point is complex prompts are a double-edged sword. What do I mean by that? We tested, for all models, we tested the difference between our series of simple prompts, kind of simple prompts, versus much more complex prompts. What we found is that, only Flanty5 and GPT-3 at the beginning weren't affected by it. GPT-3 actually, it helped a lot. For all the other models, it wasn't really the case. Bloom, again, it's a big model, so you would expect it not to be confused too much. And when I say complex prompts, I mean that instead of what you saw at the beginning, these have very big descriptions for the input indicator, for the output indicator, a lot more characters maybe for the separation between them. So things that should let the model know, hey, this is the very clear prompt structure, right? But in most cases, because the other models were smaller, it seems, they just don't manage to understand that, and it actually messes with them. I mean, this is pretty amazing. We'll talk about it very soon. Another thing, more end shots don't always equal better performance. This is quite an interesting find. So always is really important to keep in mind there. Theoretically, they should, right? But again, what we found was this is a distribution of the end shots that generated best results for one of the tasks. And basically what you see here is that for some models, 5, 3, or even 1 end shot did better than 10 end shots. Right? Again, maybe this is because some smaller models get confused if you give too much to them at once, right? I can say that, for example, GPT-3 did okay with 10 shots. This is a graph showing the performance variability by end shot. So we can see that for some models, it's very big difference between, right, like 1 shot and 10 shots. For some others, like Planty5 or GPT-3, doesn't make that much difference. Of course, when you want the best results, you will try to give him as much end shots as possible. But just saying, be careful with it. Test a bit more depending on the model. So instruction fine-tuned models shine a lot. We were really happy that we got to test Planty5 XXL, which came out just about 2 weeks ago, and found out these amazing results. Like it actually did better than GPT-3. And I want to mention here that in one of the tasks, in the named entity recognition task, it did really poorly. So that actually affected the mean score, dragged it down, because if not, it would have been even more amazing. That just means basically that it should be instruction fine-tuned on more NER tasks. But again, like, this is more amazing when you think about the fact that Planty5 is 15 times smaller than GPT-3. You can actually host this model on a 2 GPU instance. This is just a graph that shows kind of the overall performance of all the models in our tests. With a small mention, we forgot to add the GPT-J here at the end, but it kind of performed as good as Cohere, I would say. So pretty good for the smallest model. Oh yeah, and basically what I wanted to show to this was, again, the power of prompt engineering, because if we would have only used the simplest prompts, this graph would look like what you see with the red lines, right? So the performance would have went down quite a lot, even for the bigger models. So why do we bother with all of these things? Like, why do we care so much? Well, it kind of all comes down to cost, right? Big models can be very expensive to query, usually 10 times or even more than smaller models. And when you have big data sets, you do a lot of queries, that kind of can get very, very expensive. So you might think, hey, maybe I should host a smaller model on a private infrastructure, right? Some examples of this are the GPT-GA1, which can basically go in 1 GPU with a bit of Hugging Face Accelerate playing, or Planty5. For example, in our experiments, we estimate that we queried around 5 million tokens per model. And if you're interested in what that adds up to, you can see here, like, half of the cost goes basically to half of the models we tested, which went in AWS infrastructure. But I would mention here that that cost, the AWS one, maybe if you work a bit more on each model and what the actual requirements are for it, it would go down quite a lot. Because, for example, you don't need a 4 GPU machine to run GPT-J, but we kind of forgot to run it with that, so the cost reflects that. Whereas the API costs are kind of fixed; those are it. Maybe only if OpenAI decides to lower their cost again or something. Right. So some final thoughts. In terms of future work, it's quite interesting actually, because when we started working on this experiment about 2 months ago, instruction-based fine-tuning and set fit, which I'll talk about really quickly, weren't present that much. And we said, okay, yeah, prompt engineering is really like the future powerhouse and everything like that, right? We still plan to experiment with prompts and prompt engineering, but it's clear that we have to combine it somehow with instruction-based fine-tuning. We clearly saw that it won a lot. By the way, like some of the other models were a bit instruction-based fine-tuned, like GPT-3 was a bit instruction-based fine-tuned, GPT-J also, but not with the same techniques and the same amount of instructions as FLANT-5. And I want to mention set fit. Maybe some of you heard of it. It's a technique that came out recently. It kind of allows you not to play with large language models necessarily, but instead play with a small transformer and just use a few examples and get like really good results. In some cases, it beat the large language model results. We plan to write quite more in depth about the results we got. So follow us on Medium, follow the blogs. If you're interested in seeing the exact logs, results, and the code that we used to experiment, this is the experiment repository on GitHub. For all other things NLP related, follow us on Twitter. And I would like, in closing, I would like to reiterate the takeaway points. Prompt quality matters. Complex prompts can be a double-edged sword. More end shots don't always equal better performance. Instruction fine-tuned models shined a lot. And yeah, I mean, considering all that, it does affect cost greatly. Thank you, and if you have questions.
All right, thank you, Daniel. Do we have any questions? Got one. I'll come over with the mic. Let's start with you.
Thank you for the talk. I was wondering if you could give us some more detail on what constitutes a complex prompt and what not.
Right. I actually have some examples in the appendix. So, for example, this is the first prompt in the text classification. As you can see, it's quite simple. This is an example of a more complex prompt. I had to split it in 2 columns, but it's the same thing. It is the same prompt. Like, for example, you see that first at the top, it just puts the input. Then all of this basically is the test description, which, as we can see, it's quite bigger. It uses all these additional characters and so on. And it does that for all end shots. Like, it doesn't just keep the test description at the beginning. It does it for all end shots. So you can see like the difference in complexity between this and this, or even this, was the most complex one of our prompts, which I would say it's pretty simple compared to this.
All right, other questions?
Oh, and really quick, besides that, sorry, I forgot to mention, like, there's this really big repository of hundreds of prompts called prompt source. The complex prompts come from prompt source.
Yes, thanks, first of all, really great talk. I had a question on this, what you mentioned a couple of times, instruction-based fine-tuning.
Yep.
If you could elaborate a bit on it, what it means.
It's, I mean, just in summary, really quick, it means that after the model was trained, as all the other generation models were trained, with just with masked fine-tuning and things, mask training and things like that, they actually took a lot of prompts, basically. That's what the instruction part refers to, and trained the model to give the correct results based on those prompts, right? That's why you see, let me get to it really quick. You see this thing here with plenty 5, right? It didn't matter. I mean, there is a small difference, but you can see it here. But it basically didn't matter what prompt you gave it, because it was already it already saw a lot of prompts for that type of problem, right?
Right, I think we had a question over here.
Hi, thanks for the talk. It seems like you've worked a lot with several different kinds of language models, and the prompts that you've fed them have been like consistent across these models.
Yeah.
Do you think that different kinds of models will have different reactions to different styles of prompts? Because, for example, like Stable Diffusion is like it's sort of its own thing with like the image generation, but it's grown a lot, and you see that like very, very complex prompts have much, much better results for that.
Yeah. So I would say, first of all, there's quite a bit of difference between the natural language models and the prompts you give them and the visual models. They still, I mean, for the visual models, they still go through a kind of a natural language model at first, and then that gets transferred to the visual one. But what you want from it is greatly differs, right? For the natural language one, you mostly want it to understand what you're telling it to do and kind of make little logic assumptions, right? So, for example, you saw that in GPT-3, you can give it what's 1 + 1, and it will know that it's 2, right? Things like that. So it makes quite small connections. I would say that's kind of the difference between the two. And yes, I mean, it greatly depends. Like I said, you can see here, the difference between the complex and simple ones. It really depends on the model. I would say, decide on which model you want to play with, and then try different levels of complexity. Yeah, I don't know if I can answer that better. Quite a lot, I would say. I mean, you start seeing a lot of similarities between them. It's just that, depending on the data sets they were trained with and all the instructions they've seen up until now, the response will be different.
Hi. So my question is, like, if we use more than just a single sentence, like if there's a big paragraph, and we are trying to classify whether this okay, we have like 10 sentences, and if it is about data science, yes or no, you think this would work? And especially with the limitation of the maximum tokens.
Yeah,
that you
yeah.
can have.
So that's, I mean, first of all, great question. That's it really depends on the model. For example, in the summarization task, I actually can show you the results for it. The bigger the model, kind of the better it did, just because, you know, it was able to understand that lengthy prompt better. The length limitation is very real indeed. Like that's why for summarization, for example, we only limited to examples that had 500 tokens, so that we can actually give it also an example before that. You know, I would say in this case, the size of the matter does matter quite a lot, because like I had cases in the past where I was able to give GPT-3 the big version. I was able to give it, like you said, you know, a big example with, hey, do this for all 10 sentences at once, right? And it actually did. I would say most of these models up until, you know, here wouldn't be able to do that at the same time for multiple inputs, right? So that's another thing. You can actually have multiple inputs with bigger models, right? Like you could say, classify the following texts into these 4 labels, maybe give 1-2 shots as examples, then, you know, have multiple inputs, like 1, 2, 3, 4, and then, you know, just expect from it to give the responses for all of them. In the big models cases, it usually works. From my experience, from what I saw, it really messes up the smaller models. I think it's mostly the size, unfortunately, yeah. I mean, we all would like to think that, you know, you can do some very, you know, cool training to make the smaller model better. And we saw that kind of you can with FLAN-T5, right, with the instruction fine-tuning, but up to a certain point. Like, unfortunately, after, you know, adding more complexity to it means, you know, it will just have limitations.
We have time for one more question.
Have you looked at any language models that combine pre-training on knowledge graphs?
Not really. I would like to, but not really, sorry.
If you have more questions, you can ask Daniel during our shuffle time, but otherwise, yeah, we'll get our next session started in 5 minutes.
Thank you.